record this one on this computer. See? Okay, so we had an issue yesterday, but I remedied that one by going in this route that it's related to that, related to this one, okay? Because there are so many documents that to go through within 1 week. So let's clearly go through one by one. Excuse me. Okay, I want to, I cannot like this one. Can you remember this for the case study example for that our
Professor, before you move on, where is the homework saved? Where is the homework? I cannot find it.
You cannot find the homework? Ah, no.
Am I the only one that's...
Okay, I'll show you. Okay, don't worry. I'll show you. I'll show you right now. Okay, I'm gonna go here. Go to here. Okay, this one. See. Okay, go to week 1. Okay, I'm on that this module. Okay, week 1. You see, week 1 assignment. It has been made available already. This one too. Progress check 1 too. So you have to do week 1 assignment, progress check 1. And in addition to that one, week 1 class exercises we have to, we have to go through.
Am I the only one that can't see week 1 assignment?
How about the others?
I can see week 1 assignment and the file was also available for me.
Okay, let me see. Okay, if it's the worst.
Okay, just disregard. Apparently, I just had to refresh my web page and it popped up.
Popped up everything. Okay, all these. Do you see all this?
Yep. Thank you.
Yeah, one question, Professor.
Yeah, go ahead.
Here we have this data set CDBRFS10, which is in SAS 7B DAT format. Is it the same that we are downloading from that website?
Same data set, same data set.
Okay.
That's the same. That's why we don't have to worry about that. Get this one, that if you want that, if you click, see, that's the same.
Yeah, because I downloaded that, but I just wanted to confirm it's the same thing so that I don't have to go on the website and download it again.
No. You are right. Yeah, you don't have to do that one again and again.
Yeah.
So that's the same data set. This is a code book. Is important. You see, I have added something to that one because the code book have like that how they been like a description and everything. In addition to that, what you see over there, there are more other that categories being involved in that given variable. This is a chi-square critical value one. This is the homework. This is a homework 1, 2, 3. So if you go back to this one, why I cannot scroll this one? It's like it's frozen. Something. Okay. Let's see. No, this one. Okay, I can get rid of that one. Okay, then I'm gonna open again that one. No, new 25. PowerPoint week 1. Let's open this one and see whether I added something. So okay, see, this good, we got the data in. So as I said here, here. So they are copying this one, whatever the information we have on this directory or the library, they're going to change that one to this one. So here, what I did was, see, I got that one. See, this is under that, see, my shared files. That means that I can share this, all the files with my student. That means with you guys, see. So we got this one, this line. Okay, let's go one by one. So it's already, we have done that one. It's been loaded here. It's already here, I think. See. From here, we loaded here from this one. We're going to put it back. See. Okay, everything's good. Okay, see, I think that came for that pretty much everything. I was trying to run this one only. That's okay. But you see that up to here, if I run back again, that's the same thing. See? That's where that we had some error warnings because we were looking for some kind of a variable name changes, and then on the other hand, some variable has like a missing data, a lot of missing data. Those missing data, we're gonna remedy those one later on. But let's see, go ahead and see log. See, no, see? No errors. So what I did was I got the data from the transport and set, and then put it into this one. See. Then using that copy in transport to this one because it is still giving us some kind of error message. So instead of this one, we're gonna put this one to here. So it's gonna be in these libraries, both places. See? Data out, see here, as well as here too. See, both places, that's the same thing. Once you go through this line, it's already in. Then later on, they wanted us to put a data out, but that's okay. And then you're gonna set this one from this one and put onto this one. This is the new name. Sorry, the new directory. I put the data from and then extract and put it over here. See, when for that one, if you go ahead and run that the procedure contents. See? So let's say, then you're gonna get some error messages. Should be. See, some characters were present in data because some data were missing. Some data were missing. Okay. So because of that, but anyhow, on this one, we get that how many, see, how many observation, number of variables and all kind of stuff, see, their information. And on the other hand, in addition to that one, we have their information in detail, even in that this book. Sorry. Yeah. The data book. So I extracted these one. These are the one we're gonna change. Exercise. See. So this is the variable name they have given. Exercise. This is the description. During the past month, other than your regular job, did you participate in physical activities or exercise such as running, calisthenics, golf, gardening, or walking for exercise? See, there are, in addition to 1 and 2, we have 1, 2, 7, 9, and blank. See, there are 2 missing. So 1 is yes, 2 is no, don't know, not sure, refuse. These 2 not even being taken into account when you're gonna do that other thing. See, look at exercise. See, 1 and 2 only taken into account, and that should be even change their numbers. See, to 0 and 1. See, yes, 1, 0, no, earlier. Now I want to make the 0 for no. See, 2 becomes 0, 1 become 1, 1 stays the same, like that. For that kind of a changes, when you go ahead and looking into that one, that you can see that in addition to 1 and 2, there are 2 other numbers being even assigned for other categories. See, like that for that one. And the diabetes, have you ever been told by doctor that you have diabetes? If yes, and respondent for female asked, was this one during the pregnancy, like that? Blah, blah. See, 1 and 2 years. Yes, that's for the female. No, see, that's why we have taken 1 and 3, yes and no only. 4, no, pre-diabetes, and they don't know, fewer, refuse, like that. So there are so many other ways that other option as well in that one. Even on that one, we have taken 1 and 3 only. See, 1 and 3. 1 and 3. 1 and 3. See, diabetes 1 and 3. Even that one, we're gonna change that to the 1 and 0. See, again, 1, 3, 1 stays 1 till it becomes no means 0. You're gonna change that one. And the other one, what is your age? There are several that ranges. 7, don't know. 9, refuse. They starting from 18 to 99 is the one that we've been taken. We take into account. See, 18 to 24. See, several categories. So that's why I say we have taken that 18 to 99, 18 to 99. And then like that gender keep like 1, 2. I think 1 male and 2 female, it stays the same. Exercise and everything. See, gender again, if you want, it has been even added to this one. See, gender 1 and 2. See? So this everything we can get it from that book. See, code book. Code book has all the information. See, I extracted the whatever that we really need, then copied and saved that, pasted over here for your information. So then in this one, related to this one, when we go back and forth, and then homework, we can open our homework as well too at the same time. Homework, homework, see, reading Ruby, see, no, not that one. Homework, homework. I'm gonna pull out here too. We'll get the homework as well here. Oh, sorry. Here, this is the homework. Set the homework here. You see, this case study will introduce you to categorical variable and how you may use statistical procedures to investigate these type of data. Display them in a table 1 and develop results section described in your table 1. Use data from the behavioral risk factor surveillance system survey from 2010 to complete this case study, which you have already downloaded. See, briefs data, briefs data, you're going to use that one. The objective of this analysis to investigate the association between the diabetes and BMI, body mass index, after controlling for exercise and sex, that these two, see, gender and then whether you are doing exercise, those two, those are like a controlling factor, and then see that how this gonna, the BMI gonna affect the diabetes. The outcome variable is diabetes, see, and this is called the outcome variable, dependent variable, see. See? And the variable of the interest called the exposure or independent variable. See? This is sometimes called the endogenous, exogenous. See? They use like that way too. See? Anyhow, conduct a complete case control analysis of this objective following these guidelines. See? Use the row variable. See? Variable BMI for cat and then call it BMI, gender, diabetes, yes, no, like that. See? So in addition to, as I shown you over here, even for this one, sorry, this one, there might be more other that categories. We can look for that one from the code book, okay? So the front suite for the complete case analytic, restrict your sample based on the following conditions. See? Right there. See? Those are all that information, that the same thing that we are doing on here. It's an extension of that one, same thing. Let's look at this one and see that when you go through this one, see, and on the other hand, this is how we're going to write the regression model. See, regression model. Look at regression model. Diabetes, alpha. Alpha is like a slope. This one, I'm sorry, the intercept. I'm sorry, intercept. The slope with respect to age, the slope with respect to exercise, the slope with respect to gender, plus error. We have to have error. See, this is the regression model. And for y, as I mentioned yesterday, seen for y, this is the y variable, these are x variable, x1, x2, x3. So alpha, beta 1, beta 2, beta 3. This is the population. There's a model. Its counterpart we'll call the diabetes. See, diabetes estimated value. This is alpha hat. Alpha hat, you can say A. This one you can say B1, age, B2. Exercise plus B3, sex, like that, plus error or without error, like that. Okay. Perform a complete case control study using this guideline. Categorize age into 3 levels. See, like that. Categorize diabetes into 2 level variable, no and years, where years is the number 1 category of this. Categorize exercise into 2 levels, 0 and where this is the number 1 category. So that's the one that we are working on. That here. See, we got all the information. And we got the code, and then let's run on this one and see how it works. See? When you run, see? So for the homework related to homework, you can then let's see, you can, this is for that learning this stuff. Plus we can jump into the other one too. Okay. So see, for this one, see, I'm gonna get the data. See, data, see, and where, see, set data out. I get the data from here, and I'm gonna put to the here. See, here we don't have that directory. We don't have a library. We know exactly what the library is if it is not mentioned. It's the new name of the variable temp. It is in definitely in work directory. See, it's in work directory. Temp, TMP. See, temporary. See, you can get this all from the data or this way or this way. Okay, I'm showing you two ways to get this one. See? You keep in these ones. See? Age category, diabetes, exercise, sex. See? You're gonna call that one age cat. See? One, if 18 to 13, then age cat 1, age category 2. See this one. This, you know that if you have a something like this, that you can definitely get this done using even R. You know how to get this done using the entire function. Entire function, the quantile function you're going to utilize to instead of working with the numbers, you like to go to the categories. See, 3 categories. Diabetes, 3 categories. This one. See, and let's run this one. See? Then this data gonna go inside this one. See, work. You don't have to put the work dot temp. It's a temporary directory. See, they will nicely stay over there. See, those variables. First, see, already added age cat, diabetes, exercise. The changes. See, age cat, diabetes, exercise. See, now this output data. And then this going to show you that the number of rows, see, 1 through 1000. If you go to the last one, that will show you that the last 435, 5022. And on the other hand, that if you really need that to see all the columns, you can see all the columns over here. See, 2 columns. You go ahead and click on this one, and that will show you. See, display exercise. Exercise. If you click, that will be displayed. Exercise. Categorical, all categorical. Even though that data set has this a huge massive data set, we're not going to take into account that this data. Okay, these are categorical data analytics we do in this class. We don't need that numerical one. We need the categories. Even the categories involved with the number has been assigned for the category. Okay, number has been assigned for category. If you don't like that one, you can give a name for that one. You know that how to replace that one and give the name for that one. Okay, for name, see, age category. But they asked us to do 1, 2, 3. Instead that one, you can say that see, young adult, and then some old or something you can put like that, whatever that you want to put by the name. See here, like that. Yes, no. You can put yes, no. That's another way to do that one. See? So whatever.
So even though the homework says 1, 0, you don't care if we put our own description?
Yeah, you can if you want. Yeah, that homework, that if you want your convenience, it's not a big deal, but just do things in a way that more appropriate and then more interpretable and more appealing. Okay, sometimes that's acceptable because
and as far as for like answering the questions and submitting the homework, I'm assuming you want us to do like screenshots and copy and paste it on the homework.
Okay, that's okay too. Fine with that one. It depends on that how you put your one that that present that at least that give me something for me to grade it at the end of the day. Okay.
What do you prefer? I guess is what I'm asking.
Okay,
so
okay,
we run the scripts and then we generate tables. So copy and
this
paste
table,
the tables
no.
and then
Don't go
reference
to this one. This one, I don't need this output. Okay, let's say that the code would.
No, I'm talking about like the chi-square. Like I went through the homework and I got somewhat through it. So I just want to know what should I include in the homework.
I'll show you. Okay, I'll show you.
Okay.
That you can do something like this. I think that would be more appropriate to. I'll show this one. Then you can see. I have so many open here. Very hard to look at it. Okay. look at here. That okay. This if you can give in this format, okay. Let's say like this. See the code and the table. See and see code and tables. Whatever the tables that we're gonna have that one over there, just come copy and paste over there. We need the table. Then say that the second one that we could go ahead and then see after this one, see this part we really need to see. I need that code to come back again, but related to the homework. Okay, I'm gonna show you this one. See, related to this one. That's the same format here that we're gonna take into account education, then general health, and then see BMI, see the body mass index and all kind of stuff. See, give this code, copy paste on like a Word document or something, and then see give that code and their corresponding table. And if you have to.
So you said,
go
sorry,
ahead.
so just to confirm, you want us to copy the code as well as the table?
Yeah, you copy the
Okay.
that code on that like here that this one. Okay, let's copy this one. Okay, copy and
Okay,
paste
I
on
got
like a Word. Okay, and when you run that, when you get the results, copy that one, that table, and then paste on that one too. Sometimes you have to write the description. Then it's easy that keep everything in the title that in a one file. That's gonna be very easy. Okay, when I come back to here, see, you can see that what I have done over here. See? Then if you want, you can put the question very nicely and then their code and then their results, see, like that. See? Then sometimes that you have to do by hand something. Then you have to make the table, do by hand. See, we're gonna talk about that one. So this kind of this format, it's easy that this has been done, that this has done on like a MS Word, and then you can convert that to a PDF later on. See, this are, see, you wrote that one. See, this are like,
So it looks, so if I'm understanding correctly, the purpose of this is, well, this particular homework assignment is to calculate the chi-square to see if the variables listed in the homework are statistically related, right?
exactly. But we have to go to that theory because there are so much involved in this class. That's why this is normally done in like a 15 weeks. Material being condensed for 4 weeks. That's why
Yeah.
that yeah. So that's
do
the
you-
rough
do you-
idea. That's the rough idea. Yeah.
Okay, so do you particularly care? Do we have to use SAS? Like, because I'm more strong in Python. If I can
Okay,
still
no,
generate
Python
a
go
complex,
too. Go ahead. Python use
awesome.
that one. That's okay. That's okay because you don't. If you really want to learn this one and do that one in SAS, it's no. It's all about that. How you're gonna do the things in that any of the languages. It's okay.
Okay,
That's
thank
fine.
you.
That's fine. Don't worry.
Do
Okay.
you still want my you want my Python code as well?
Yeah, Python code. If you can do in
Okay.
Python code, that's okay. Okay, don't worry. As long as that I have like a, let's say that chi-square value. This value cannot be different from the other one. Any programming, it should be the same. See, like
Yeah, I got
ratio, continuity,
Okay, I got you.
mantle Hensile, that one. That's because we're gonna do that comparison and contrast based on these values. Okay. Yeah. Do use anything that's convenient to you, because even in this class we are using R codes as well too. That R and Python, anything. R, Python, SAS, anything. Doesn't matter. Doesn't matter. Okay. So this is the kind of format I'm expecting. See, if you want nicely, like you put the question and then put the answer right below that one, and then make a nice document and then plug that send to me. Okay, that's the same thing we have over here. See, up to here. So when we run this one later on, this is one way of that, keeping that all the variables. And another way that you can just do that one temporarily, that's temp. Okay, the TMP, I use that one here, TMP. See, age, see, another way to format that one. Keeping all the variables like this. See, these variables are taken into account, and do the same thing that we did over there. And then I'm gonna run this one. Temp that one. See, then you can easily see that what are the changes that you did for those variables. They will be displayed. See? And it's gonna go to this work library. See? Temp. Earlier thing. Either way is fine. Either way is fine. See? And then you can check that their contents after that. This data. See, that data has only 4 variables. See, that data has 4 variables. That's a data frame. See, 4 variables. Yeah, information even here. So later
What's
on.
your language of preference, Professor?
Which
language do
either any language, R, Python, SAS, anything you use, that's okay. Any language, okay.
No, I'm asking you in particular. What's your favorite? What do you prefer?
I use the 3 of them for time to time for different problems. Python is that most favorite, the favorite one, most favorite one, Python.
My man.
Because you can do a lot of stuff from that Python, no, that machine learning and all kind of stuff, the heavy stuff. So when it's come to the, because we were doing heavy research, I use all the time Python. Python is the one. The SAS is kind of like a packages. So that's okay. We can learn that one, but Python is the I think so far the best. And there's another one, Julia. Have you ever tried that one?
I haven't, but I've been looking at it. It seems like it's comparable to Python, with like a few changes.
Yeah,
right?
if you go to that, if you go to the Anaconda Navigator, in the Anaconda Navigator, you can have R, Python, and Julia. Everything can be embedded over there, so that you can interchangeably.
Is that available? Is Julia available in Anaconda?
Yeah, Anaconda. You have to install that one, Anaconda. Same way like R, you can.
Yeah, we have it. Well, I have Anaconda. I think everyone should have it.
Yeah, then you can get the Julia on that one too. Just go ahead and check that one, how to get that one into that, especially that Jupyter notebook, into the Jupyter notebook. That ID, yeah, that's the one way to get this done. Okay. So then let's see that here they were asking about that. It will go further down. Okay. As we had a discussion, we can build up that frequency table. It's called the frequency table. How do you put up the frequency table? See, look at the frequency table only for this one. The respondent, their gender. See, like that. See, frequency, how many people, how many male, how many females, and their percentages and cumulation. See, this number goes over there and then will be added to this one to get this one. Will be added to this to get this one to complete the total number of observation, no total number of respondents in this particular data set. As a percentage, this, see, this number, see, this number divided by total, this number divided by total will give you the percentages. And then later on, you're going to add this percentage to that to get the cumulative percentage. For the same,
are those percentages what we use for our estimated?
No, these are actually, that's a very good question. Actually, that since we are working with this, all the data, these are all estimates. These are estimates. They are that corresponding for population version we don't see here. Actually, we are always this data, when you work with the data, we are all estimates. You can simply say these are estimates.
But that's not the one that we use, correct? We use more of the R squared.
Oh,
no, I'm talking about the So I was talking about the manual calculation of chi-squared.
Oh,
yeah,
manual
so
calculation.
It's observed minus expected squared over expected.
Yeah, that one we didn't come to that one because this is not a contingency table. This is just like a frequency table.
Oh, I see.
This is still we're not there. We come in there. See, 2 variables come into that one. Then it's automatically become a contingency table or the confusion matrix. Then you talk about there's any association between this guy and this guy. Exercise and the age has any association. That's the same thing we did earlier in your previous class, but both of those variables are X and Y, both are quantitative. Then you use the regression. Now we are using that the procedure, the contingency table procedure, and then the Pearson that chi-square test and Fisher's exact test based on the given condition. That's why.
Professor?
Go ahead. Go ahead.
My bad. I didn't mean to interrupt you.
No, that's okay. Don't worry.
I just forgot to ask yesterday when you were talking about contingency tables. You do something very similar to that after you run a random forest. Is that at all related?
Yeah, this is the contingency table. You can see this is the contingency table. See, you have a 3 options on this side, 2 options on this side. You're gonna put this one here. See, in the middle, you have a number. That means the age category for age category 1 people who has say that no to exercises. See how many people.
But is
You're
it called?
You're,
But
you're
is it?
talking about a
Yeah, okay,
confusion
go ahead, Phil.
matrix. You're talking about confusion matrix. Though. That's
Okay,
not
yeah,
this.
that's right. Okay, cool.
No,
Getting a little-
contingency table and confusion matrix closely that we're gonna call the same thing. See,
Really?
yeah, see.
Yeah, because you were going over the contingency table. I was like, I do that or something similar after I run every random forest.
Yeah, this all are contingency table. These are contingency table. See, these are contingency table.
Well, you
That's
don't
the
really
same-
run it, I guess. The random forest generates one of those if you do
No.
it properly.
No. We don't go in that route yet because that is the primary stage, because we have to slowly then steadily tackle this one, because even in the contingency table, you
Okay,
can.
I'm not trying to get ahead. Sorry.
No. That's okay. That is we're fine with that one. But I'm trying to say this involved with so many things. See, so many tests, so many things. You look at this. Everything you have to get a clear idea what this means. Why we go to this? Why we go to this? Why? Because this everything can be taken into account in order to run the test at the end of the day. What test we are talking about at the end of the day? You have to write the conjectures very clear cut. Why we gonna go to the Fisher's exact test? Can we get this done by hand? Where are these numbers coming from? That's you have to know everything. That's why this is very challenging, because within a short period of time they have delivered so much material. It's not about simply that write in the code. Write in the code, it's okay. See, this one they say don't even do by by running that one. When you run, you get the answer too. But here, related to that one, we can get to that one too. See. So here, look at the second one. Second one, see, the table exercises was age category. See, age and this one. And then we're going to say, don't put the percentages, don't put the row percentage, don't put the column percentage. What this means? Let's go ahead and have a look at it, what that means. Little bit real quick. Yeah. Okay. See, then we got that one. We're going to get the frequency table. See, frequency, you get the table. Go to the data, you get that one. You need the table for this gender. See, you run this one. See, that's the same table that you saw earlier. See, these are the frequency, this is a percentage, frequency percentage. See? Like that. Let's do something like that. This one. See, if you say no percentage, let's say that what's going to happen. No percent for this one. See, they were taken out. See, so you can have a percentage or no percentage. See, no percentage. But that's a frequency table. That's a frequency table. See how many these people see for this one. That's what they were primary stage. They are. See, later on, they're gonna have they're gonna build up the now contingency table. See, exercise versus age category. See? It has pretty much everything. See, look at what happened. What this number? What is the second number? What's the third number? In each cell, these are called the cells. These are 2 by 2, 2 rows, 2 columns. Sorry, 3 columns, 2 by 3. I'm sorry, 2 by 3. See, 2 rows, 3 columns, 2 by 3. Each inside cells have see different number. This is the number. This is what is this one? This is the probability percentage. This is a row percentage, column percentage, like that. See, you can see that the 220, 2.20. That if you want, you can have those numbers. See, 9,554 divided by 40,500. That's if you do that one, look at it. 49,554 divided by 435, 43, 50, 22. that give you that 0.021. See, that means 2.20. That's that number. See, this number divided by the total. This number divided by the total will be the first number. This number divided by the total, grand total. These are called the row totals, column totals, percentage. The same number being divided by the total. See, as a percentage. Then they will add to 100. Same way here, 119,093 divided by 43, 135,022. That will give you the percentage on this one. In addition to that one, on this one, look at the 8.02 and 20.06. 9554 divided by 11,099, that total, let's say 9554 divided by 119, 093. See, then you're gonna get 119, right, 9554 divided by 119, 493.08. See, 0.08 means this one, 8.02. See, that's the row percentage. Row percentage means that this divided by this divided by that, this divided by that. That's the second one. The third one is this number divided by the column total. 9554 divided by 46,381. Yeah, that's the 20.60. See, that's the row percentage. Sorry, column percentage, row percentage, cell percentage. This one row means like this percentage has been divided by this one. See, and like that. If you don't need that one, see, you have to tell that one. See, exercise, see, age category. You don't need that one. Get rid of that one. But we still have the row marginals. These are called the row marginals. See, row marginals. See, column marginals, and the grand total right there.
So, Professor, for the manual portion of the homework, we can do that in Excel. We just show the values.
Yeah, that's fine. Yeah, to do that on in Excel and then get the answer and then put it over there and like that. Okay. So then that's pretty much the same way that if you go to the, see, by controlling then this one, see, rows, columns, and then you're going to add another one to this one. Look at now. Systematically, you're going to add something. Look at what we're going to add over here. Okay. So the exercise by gender, let's say the same thing. I'm going to add measures. What are the measures? What that means? See, there's so many, see, ways to get this done. So we have to have a clear idea what is gamma, Kendall's tab, Kendall's tau, that see, tau. Okay, I'm sorry. Kendall's tau, see, Stewart's tau, Summers, Pearson correlation, Spearman correlation, lambda symmetry, uncertainty, all these. In addition to that one, odds ratio, relative risk, all these you can easily generated by running that measures. But we systematically learn about that, what this means, get a rough idea. Okay, rough idea you really need. See, and then at the same time that you can talk about that these two tables at the same time. See, two tables at the same time real quick. And from this one too. See, and then I put the chi-square. That will give you, see, testing procedures. See, testing procedures, chi-square, likelihood ratio chi-square. See, Mantel-Hansen chi-square, phi coefficient, contingency coefficient, Kramer's V. So many ways to get this done. See, the table will come along with that. See, age category and this one. For that one, for this one, gender versus age category, and this one for the exercise versus the age category, same thing. See, whether there's a correlation between these two or not, there would be any association would be between these two or not, like that kind of a discussion versus its counterpart, which is the natural alternative hypothesis, would be they do not have any correlation, no association between those two. If there's an association, how strong the association would be. Can we get those kind of information? Yes, like that. See? That's something that this is same thing being that extended to this one. Later on that they have they run that logistic regression. Logistic regression means this one. See, why it's logistic, categorical. I don't worried about this one. I'm worried about this guy. This is categorical. This is categorical. Why variable is categorical? That's why I'm using the logistic regression. You can remember that yesterday, that in a chart that, sorry, not this one, lock it and then.
So we use the logistic regression. What should we focus on from that table? Is it again just the
Yeah, the logistic regression, that's the part that we're going to run that at the next step that I want to show you something.
Okay.
Okay. Then run and get the information, and then with the information that we can you see, can you remember? See, quantitative, explanatory variable, X variable. See, quantitative, and the category response variable. If it's categorical, you have to use the logistic regression, discriminant analysis, and all kinds of stuff. So see, so logistic regression. That's the part that we were trying to. Sorry. See, we're gonna keep the reference this one as a real diabetes 0. Exercise reference, you're gonna keep the 0 with respect to that one. How the other's gonna changes. So they're gonna keep this one as a, like a basis. It's the basis. See, reference 1 here, reference 1. See, logistic. See, that will give you the information for you to see. Those are, see, all information. These are what? These are degrees of freedom, estimate, standard error, chi-squared, probability, that the p-values. You really need, then this odds ratio. What are those ratio? We have to look into that one. Then association of predicted probability, see, concordant, discordant, see, everything we have to have a look at it at very clearly over there. See, here mainly that this is the B node. This degrees of freedom means independent number of pieces that can be utilized in order to estimate something. So it is 1 because it is just a 1. See, intercept 1, age category 1. See, this one 1, this one 1, this one 1, and they are estimate. These are the B node. This B node, in this one B node. This is the population. This is the population model. The population model. See? First, what we're gonna do, the theory I'm gonna do tomorrow, add to the Friday, add to this one, and then to continue this discussion. But for time being, let's try to get the answers for this question first. Let's see this one. See, this is alpha. Alpha I can call A. Its counterpart in the sample, estimated one is called A. This guy's estimated value called the B1, B2, B3. Those are the values we can see here. See? See? What is standard error? What is the standard error? Standard error is the standard deviation of this guy. Now you might be thinking, how come you have a standard deviation for this guy? It's a fixed value. Fixed value how come that carried it? This broader discussion, if you cannot recall, enough 600, 605, 620, we did in a broad range, this discussion. The standard error. By telling that how they're going to differ from, you don't have only one, you do not have only one B1 or one B2, one B3. These are the observed one. Observed estimates. In addition to observed estimate, think about that someone else has taken the same data set. This estimate not going to be same as the estimate that you see on the screen. That difference, let's say another person going to do one, the third person, fourth person, fifth one, 100th one, millionth one. If all same person going to do this 1 million times, they do not produce the same answers for this estimate. They differ. That variation called statistics. That variation is the one that we try to tackle all the time in data science and data analytics. See, that variation in the problem. When the problem being given, that there's a variation. Because of the variation, variation means the error. Error has to be minimized. How could we gonna do that one? That's why we call this one even standard error. That means that this value you can put it into a histogram. Put it into a histogram. On the histogram, you get the smooth curve. From that smooth curve, you're gonna go to the middle of that one. That's get you the estimate. Out of all the estimate, you get that estimate, plus you get the standard, the spread of the histogram. That's called the standard error. That's called the standard deviation of B1, B2, B3, B4. And what is the chi-square? Chi-square means that when you, based on that one, that's a test variable. That's the test variable. You have seen that this kind of stuff in that previous classes. That's like that something. I show you this here. They say that from the population. This is a population. See. Let's say that's it. Yeah, this one. This one. See. From this one, if you pick a like a say, sample, from sample, this is the population. You pick a sample, and from the sample, if you calculate, let's say B1, and again another one, another B1. It's the first B1, there's the second B1. And you keep going. Let's say that you're going to do that 1,000 times. B1000. This is all the 1,000. This is see, sample 1. You have a sample 1, sample 2. See, you can generate samples. And in addition to that one, you have your observed sample. See, that's the observed sample. See, that's the briefs. See, that one. That sample you calculate to B1. B1 calculate, you can call that one observed. See, that's the one we're going to utilize. But these everything gonna differ from each other. That one you can put it into a histogram. See, B1. You can draw a histogram for B1. See, see. You can draw the histogram for B1. See, and draw a smooth curve on the top of that. And you get the center of that one. That center would be nothing but your B1 obs. That's what they say. In addition to, you have a spread. This spread is the standard deviation of B1, which is called the standard error of B1. See, standard error, that's spread. Oh, that's all the B1. That's the one you're gonna see over here. That's the tricky part in statistics. Even though you have one number, that number coming from the center of that particular distribution, histogram. You have to draw a histogram for all the data. From the data, that this whatever you see here in the estimate would be nothing but the center of your histogram. This is nothing but that's the spread of your histogram. This is the testing variable that you're going to utilize and see whether age category, the exercise, gender would play a heavy role in order to explain that whatever the variable that we have that taken into account. Sorry, the I think body mass. What is the variable? Diabetes. See? Would these variable gonna explain very clearly that diabetes? So are they important or not important? If they're not important, you can take them out, or whatever the other variable you have to add to, and you can remodel this one. That kind of a discussion we built up over here. But while we are doing that one, we have that the issue is that these come in that these are that sometimes you're gonna say age and exercise, are they interact each other? Why we gonna check that interaction between these? These are called the multicollinearity. Multicollinearity means like these are independent variable. Try to interact each other rather than interacting with this guy. You should have been interact with this one. Then they're gonna interact with each other. See, age gonna see age and then exercise. Would they interact? See, age, exercise and your gender. See, that kind of a discussion you can build up too. See, so here see various ways that if you go see exercise and gender. See, exercise and gender. See, exercise and age and all these, are they interacting each other? Are they independent from each other or are interacting? That's the discussion you built up first before you move on to this history of this one. We move on to this logistic regression. See, these are these interacting exercise and age category. See, exercise and age category. Age and we're gonna call that one age cat now. Age cat and you see exercise. Are they interacting? See, are there's any association between these two? If there's association, it creates a lot of problem that we have to make sure that association is not over there, because we have to make sure without and independently, these will explain this one. That's why we're gonna go step by step. First, we're gonna say, okay, let's go ahead and then have a table for this guy only. Then have a table for these two. Then we have a table for these two. And not only table, those are called contingentable, and see whether there's association or not, based on the different parameters. And later on, all these three together have any correlation with this diabetes. That's the kind of a discussion we are building up over here. That the thing is that we are dealing with categorical data, not this quantitative data. Quantitative data discussion you have heavily done in 620. So that part. So up to that point, that if you go ahead that one, the similar fashion that if you go there now, let's pull out that our homework. Okay. And where's the homework? Pull this out and then run over here. Okay. RStudio, yeah, that's good. Okay, then look at that first question. They're gonna ask, use these categories. Okay, let's categorize that one too. Okay, let's categorize that one the same. Let's try to do that one. Do we have that one, or can we create a new one? I'm sorry. This one can say homework one. One. So it's the same way data work. Okay, what the data. Data. Okay, we have this one. So we're gonna keep this one. Have you ever been told by the same thing that we had for the other one? Okay, diabetes, this one, but physical activities, gender, 1 to female, then set we change to 1 0, BMI, and run. No, those are the major ones. You have to have the age category. Age, did we change that one age category? No, for the complete case analysis, restrict your sample based on the following category. You don't have to categorize the age, no? You don't have to. Age gonna go from 18 to 99, see? 99. And this one, 1, 2, 1, 2 has been now changed to, see, gender has been changed to 1, 0. Diabetes 1, 3, 1, 3 has been changed to 1, 0. Exercise 1, 2. 1, 2 has been changed to 1, 0. Education. You have education 1, 2, 3, 4, 5, 6. We keep that one. General health. Be my cat 1, 2, 3. We're gonna pick put the name. See, as I said earlier, you can give the normal, overweight, and obese like that. See? And you can call that one BMI simply. What else? General health. We keep that one. 1, 2, 3, 4, 5. We need the 5 categories. BMI 4, row that you need the 1, 2, 3 categories. Body mass index. Gender, you need, see, if you go ahead and look at that example for the complete case and sample based on the following condition. Age has to be going from 18 to 99. Gender has to be 2 categories, see, 1, 3, and row categories 1 and 2, 1 and 6 education categories. Education like that. Okay, born in one word. What is the one? Oh, why? Oh, sorry. We have to get this data. Okay, from this one, let's get that one. Say data out. You can see data out. It's easy. Data out. We already have that one. Data out. Dot that one. See. It has that one. Why doesn't that one? Oh, damn. Oh, this one we don't have. The sorry. Oh, CDB we don't have. Output. This one go to 10. Ref. Why not? We cannot read from that one. So we have CDB F1. Hit the data and then set this one to temp. By accident, okay. To run that one. I think by accident I ran that one. They should be replaced. Let me see. What's the problem here? Errors one error output. Refresh output is not. Oh, I'm sorry. It's not output. Yeah, that's what. Data out. Right. This one. Yeah, this put here. By accident, I put this one here. So this we get that one. Then mainly what we are trying to do, let's go through all the answers today, and then the background behind that one we can discuss on Friday, and then strengthen the whole discussion. That's what I plan to do. I'm going to work with this one today, and then if you get a chance, that even that in class exercise as well. Okay. So later on they ask us to, what's the next question? What they asked us to. Using the frequency, show that simple frequency table for gender, exercise, and BMI. You need only the frequency table for all these. Just the frequency table, not the this contingency table. Okay, one at a time. That separate. No. Yeah. So I'm gonna get that this one. See, tables for gender, BMI, for cat, exercise. Those four, I think, for these categories, they ask us to find the gender, exercise, and BMI. Cat, gender, BMI. Cat has been changed to BMI. Gender, where's gender? Okay, gender here. Exercise is at the same name. BMI cat. You need the BMI. Yeah, so these are the separate that frequency table. If you don't like percentage, as I mentioned earlier, you can put no percent. Okay, so no percent over there. See, you can have 16,000 like that. When you're going to give the answer, just as I said earlier, this copy this one and paste over there. Then along with the code, get the code and copy this one and get the Word document and then paste it. And if you want, you can write even the question number. See, that's the question number 1. Okay, 2. Using the frequency, create a 2x2 contingency table for exercise by the gender. See, it shows only the count in each cell, only the count only, that they don't need what? They don't need the number of rows, number of that no column percentages. Can you remember? I showed you earlier column percentage, row percentage, percentage. They don't need that one. And using proc. Okay. So you need the exercise by gender. Exercise by gender. Number 2. I'm gonna make sure that I'm gonna label it later. Okay. So tables. Go by the exercise by gender, and you're gonna give even the chi-square, no row total, no row proportion, the percentage, no percentage, the total percentage, no column percentage. Okay. In addition to these ones that we can talk about a little bit later, see, chi-square, likelihood ratio. Chi-square test is the main one that we're going to utilize. When it's a certain, under certain condition, we go to this one, and this one, and this one. Okay. That one. So you saw that result. See, this is the table. See, 2x2 contingency table, gender by exercise. Okay. And we're gonna see gender and exercise interact each other by we are trying to do gender, exercise, and then what are the variables we're gonna utilize in order to talk about that the body mass, the BMI. Sorry, the objective analysis to investigate the association between diabetes and BMI. See, mainly see diabetes and BMI. See, body mass index and diabetes. for that one. Then show your hand calculation of the chi-square statistics for the testing whether there is an association between the gender and exercise. That's where that we have to that little bit talk about that hand calculation. How could you gonna do the hand calculation? In order to do the hand calculation, what we are supposed to know over here? What do you mean by where these ideas coming from? So we have to make sure that we do the right thing over here. See, when we have the contingency table, what kind of a discussion we can build up over here? See, what kind of a discussion? So, what is the test statistic over here? What is the test statistic? They're gonna show you calculate chi-square statistic for the testing whether there's an association between gender and exercise. Gender and exercise. So, what would be my null hypothesis? See, you have to write very clearly null hypothesis. So you can say there is no association between gender, sorry, gender and exercise. Versus its counterpart, natural alternative hypothesis, we can say there is an association between gender and exercise. See? So when you have a test, these are see first step, you see, write the hypothesis or conjectures or propositions. Then second one, but you really need a what? Test statistics to run this one. Test statistics. Here we are using, see, x squared, see, Pearson chi-squared, x squared. We're gonna say this one is nothing but summation, double summation, because we have rows and columns. Double summation, see, we can say, we can get this done in two ways. Like I see, we're gonna write here R ij squared. I maybe I goes from I for the rows. For the rows, you have what? Rows you have that 0, 1. See, 0, 1. J for the 0, 1 as well. See, these are for the rows. These are for the columns. See, Rij. Oh, same thing. I'm gonna write with the single summation. See, and put I and J at the same place. See, they both will take. See, simply put I and J. You know, I can take what? I can take 0 and 1. J can take 0 and 1 as well. See? And Rij square. Where Rij means what? Oij minus Eij over square root of Eij. O means like an observed value on the observed value in the that ith row and jth column, or first column and first row. They're like that. Ith row, this one for ith row, this one for the jth column. It's the expected value. Ith row and jth one, and divided by the square root of that one. If you put this one, that's the same thing. We're gonna write, if you put this back into that one, it's the observed cell frequency. I'm gonna say cell frequency, cell number. Is the ij, sorry, observed ij cell frequency, ij cell frequency, ij cell frequency. This one expected ij cell frequency. It's called the frequency number. It's easy. See, frequency. See, if you put this one into this one, you can simply say your test variable is chi-square. Chi-square in that printout you saw chi-square. That's the chi-square they are trying to get that one. See, I'm going to put x squared summation I, j both I and j both here. If I plug in this back into this one, it's nothing but OIJ squared minus, sorry, OIJ squared minus, sorry, OIJ minus EIJ squared over EIJ. See? See? IJ. See? They think, okay, look at what I'm going to write this one. They think this is distributed. Tilde means is distributed. Is distributed according to chi-squared. See? It's called the chi-square distribution with the degrees of freedom, df. df means degrees of freedom. That means independent number of independent pieces of information. Number of independent pieces means pieces of information utilized to estimate the unknown parameters. Unknown parameters means population mean, population, anything related to population. See, population characteristics. I'm going to say population characteristics. Population characteristics. The degrees of freedom is given by here. See, row, number of row minus 1 times column minus 1. R, number of rows. This one, number of columns. See, that's how they get the degrees of freedom. So this one behave like a chi-square distribution. Now we have a question. Chi-square distribution means how it looks like. See, it looks like, see, if you put the x squared here, if you draw the frequency here, it's a histogram, another version of histogram. See, frequency, instead of frequency, I'm going to put the relative frequency. Relative frequency means nothing but probability or percentage. Same thing, percent over here. And then if you draw the histogram, then it looks like, and get the smooth curve scheme in the top of that one, it looks like that. See, if you draw a histogram, how could you gonna draw the histogram? You can generate data. We're not gonna pick the data. We have only one sample in our hand. But we built up the theoretical aspect has been built up as if this being taken by some other person. How could it gonna vary? That variation has to be tackled. That variation is displayed on a histogram. That variation is displayed on this curve, density curve. This is called the density curve. And these are well-established curve. There are more than 300 distribution being put forward into statistical arena. This is a chi-square distribution. See, chi-square degree, the degrees of freedom distribution. I'm going to use this abbreviation to say distribution like that. See? Then in this distribution, if you go ahead and mark somewhere, see, you can see your chi-squared value. I'm going to denote by O. Okay, I'm going to denote by this one. I'm going to say my observed or calculated chi-squared value. See? That's the value. See? The observed value. Anything, any chi-squared value, x squared value, I'm sorry, x squared value, you're going to find more extreme than this one. See, probability, see, that any x squared value greater than or equals to the observed value. See, it's called the p-value. See, probability that any x squared value extreme than x squared ops value is called the p-value. That probability. That's called the area under the curve. See, that's the area under the curve. It's the p-value. P-value is that area. That's why you're gonna come all the time. See, p-value come along with that one. See, p-value is nothing but the observed value. Observed value we are coming from to observed data. Observed data already generated chi-squared value. P-value is what? How do you get the p-value? With the aid of this distribution. They have done everything for us. We're not going to do anything by hand, but in this particular case, they tell us to calculate this part by hand. This part by hand. Okay, that's the way that this homework has been set up. Okay. They say that, see, sorry. So this one, show the probability, show only the counting itself. That shows you hand calculation of the Pearson chi-square statistics for the testing, whether there is an association between sex and the number one part B. See, based on your calculated chi-square value, is there any association between sex and exercise? Explain what is your null hypothesis, what's the significance level assuming, what's the critical chi-square value, what is the conclusion from your statistical test. See? So in order to that one. So that one. So we already see the null hypothesis. Right? Null hypothesis. Then test statistics. We're gonna build up that one over here, all the way up to here. Okay. Then this one is the calculated one. This one, see, I'm sorry. So this one you can say observed value. See, observed value is this one. That's why it's not value. See? You can calculate that one. You can do by hand. In order to do by hand, what are you supposed to do? See, how do you get the expected values? How do you get the expected value? Let's see the expected values. You get the expected value. Okay, if you can see, can you make a see? Make a table like this. Now where we have a question, how to get the expected value? See, what do you get the expected value? You're gonna multiply this row total and column total and divided by this one. No, you know how to get that unexpected value. I'm sorry. Here. So we can see that one. If you wanna somewhere, if you wanna the idea about that one. Duffy, let's go to Duffy one. So here, okay. OIJ. Oh, sorry, here. Let's see here. Okay, convenience. Expected number of subjects who receive the drug and negative outcome. See, drug and negative outcome. That's mean this one. If you want to get, this is the observed value. Expected value, expected number of people who are going to take the drugs and then have like a negative value, like in this particular example. Okay, so what are you going to do? You go to this one. Yeah, their total, the percentage as a percentage, if you can do that one, and multiply by C. So you can get the percentage and this percentage multiply together and then multiply by the 150. So this total 75 times 80, see, row total, column total, and divide by the grand total. That will give you that cell of expected value. Cell expected value. Let's say that 30. 30 times. Okay. 30 times, I'm sorry, 75 times, 75 times 80. 80 divided by 150. 40. See, that's how we get the 40 in another way. It's easy that rather than going with the percentage, you go the see row value. See row total. How do you denote the row total? See row total times the column total. See this is the row total and column total, and then divided by the grand total. So in this one, see, so that would give you the expected value. So once you get the expected value, you can write along with that one. If you want, put comma and say expected value, or the way that we have shown over here. See, you can put like this way, like make it like a table. In this particular case, how do you get that one? 39,424. That's you see, this is a row total 111,531, 111,531. And multiply by this one and divided by this one. See, put that, see, that will give you the observed number of expected number of the people in that cell. The same way here, see. So that means that you have to show you over here. If you're gonna, I'm gonna write this cell, this contingency table. In a general case, if I do this one, see, I'm gonna say you have N11, first row, first column. This one, 1, 2, first row, second column, and second column, second row, first column. N2, 2. Those are the numbers that you have. See. So then N11. Then if you have the row total, you can say like this: 1 dot. See, 1 dot means a row total, first row total. 2, second row total. Dot. And this one, first column. See, total column, first column, total, second column total, then grand total. See, grand total. So 011, see 011. If you want, they put this one. I'm gonna see 011 observed. Okay, make it N11 easy. 011 observed. 011, 011, O. Then NO total O. So your E11 would be what? O1 dot times O dot 1 divided by O. Then E11, E12, first row, second column. That is O1 dot times O dot 2 divided by grand total. Grand total we're gonna denote like this way. Or if you want, you can go with the N11 as I put. Okay, either way is fine. N12, N22, N21. This one N1 dot, N2 dot. This one grand total. This one N dot 2. This one N dot 1. Either way is fine. And in the fashion that if you get that one, you have all these. See? Like this. You have a this and that. Now you get the, see, you're gonna go ahead and find the difference and square. See, get the difference. Either way is fine. This minus that. See, make a table like that. Okay, table like that. See, observed value, expected value, expected, observed totals, expected totals, observed total, expected total. See, this one total, and this way, see, 413,748. Then the chi-square statistics found by first computed for each cell the count. Observe this one each. Then second summing this count across the cells. So in this case we have, see, this one, and this one. Is that the value you can see here? 979. Do you see that value anywhere? Okay, let's go over here. Sorry, This one, what happened? Okay. So, remember that and we put the chi-square too, no? See, chi-square we ran that one. No, Apple. Table. They're not gonna run. Data temp. Okay. This one. Okay. That's okay. Let me see. Then I will say data out. No data out. Oops. Mhm. Let's get 979, 979.0102. See, that's the answer. See, that's how they calculated too. See, that's how they calculated. Even from the program, you can easily see, but in this homework, because I didn't make this, any of these, I didn't write all these exam, they were already uploaded into the system, see. So they want to know that whether you know this one, how to get this done. That's why they want you to do by hand, see, by hand. But when it's come to the degrees of freedom, but in addition to that one, look at here that see, chi-square, then likelihood ratio chi-square. Likelihood ratio chi-square means like another version of that one. Why we have to use that one, likelihood ratio chi-square? See, later on the continuity adjustment for the chi-square, some kind of adjustment. This is see, Mantle Highness chi-square, the phi coefficient, contingency coefficient, those things. So let's have a look at this one real quick. Not this one, okay, this one. Go to this one, regression, no, Duffy. So And in order to see, here very clearly say something. See, what is an adequate sample size for the chi-square test? The expected value in each cell, expected value in each cell should be more than 5 or ideally more than 10. See, it has to be. It has been taken from this textbook. This textbook is being recommended. Stocks one. See. Stocks. That textbook, the other textbook, okay. We see above that expected cows in 35 plus in this case, okay, that this particular place when they calculate. But if you don't see that one, see, if you don't see that if this minimum is not met, then the Fisher's exact test can be used to test the association. See, association between those two. See? So first level, is there any association between the gender and exercise? See, okay, there's a null hypothesis that the exercise is independent. There's no association and the excess frequency are the same. To reject the null hypothesis, we must find a chi-square statistic that exists a critical value pertaining to given p-value, assuming that significance level of 0.05, finding degrees of freedom. See, how do you find the critical value? See, so you can get this done in two ways. See, that for this one, after that one, what is your null hypothesis? What is the significance level? Significance level, we talk about 0.05, okay, 0.05 alpha. Okay, what is the critical chi-square value? How could you gonna find the critical chi-square value? You go to your table has been given, no? Can you remember? There's a table has been given, chi-square table. See, chi-square table. Look at the chi-square table. How do you get the critical value? What that means? This is what we are trying to say. We know that p-value. Can you find the p-value? Can you find the probability more than that one? See, more than the observed value. So you can do this one in two ways. See, two ways. You can go to this chi-squared one. See, x squared value here. You go ahead and say this is your observed value, which is 900. You already found that one. 939.9, 979.010. So you're gonna see the probability. See p-value. You can look for the p-value. P-value is nothing but probability. This chi-squared value, x squared value greater than 979.010. That probability. See. So can you find that one? Can you find the probability greater than that one? If you know p-value, if p-value, then you can say if p-value is extremely small, it's called the decision rule. You're going to get the decision rule for the hypothesis testing. If p-value extremely small, p-value is less than level of significance. Level of significance, which is alpha, in this case 0.05. We reject H naught. Reject H naught. Okay. Decision rule 1. So second one, if observed chi-squared value, I'm going to take this one x squared naught greater than critical chi-squared value, sorry, critical. See, that's this one, critical chi-squared value. I'm gonna write this one chi-squared. I use the chi there. Chi-squared with the degrees of freedom. Critical value with the alpha. See, that's how you denote that one. You reject H0. See? You reject H0. Reject H0. What that means? That means you're gonna find, see, you have this one. So you have now this time area has been given to the right of that one. The alpha being given, I'm looking for this guy. This guy is called the chi-squared degrees of freedom, which is in this case, see, row -1, column -1, which is 2 minus 1 times 2 minus 1, which is 1. See, comma, alpha is 0.05. 0.05. See, that means your chi-squared 1 comma alpha 0.05 should be found from the table. See, or from the SAS you can find too. See, so this region we're gonna call the rejection region. Rejection region. This region we're gonna call the acceptance region. See? So chi-squared 1, this one is 1. The degrees of freedom, comma, how much of level of significance that should be given over here. See, that value has to be found with the aid of this one, degrees of freedom, 1, comma, 0.05. Can we find that one from our table? Our table. So for this one, see, chi-square table, degrees of freedom. New means degrees of freedom. They put the alpha first, that's okay. See, alpha should be 0.05. See, this one, 3.841. 3.841. So that's value. See, degrees of freedom. This alpha, they put the alpha first, okay, but that's okay. Alpha means a level of significance, 0.05. Okay. See, then this one, degrees of freedom 1, 3.841. Okay. So I hope this area has been given to the, I want to make sure the table gonna take the area to the right most that area to the right or left on this one. I didn't say clearly. Hopefully this one is consistent with what we have rather than the other way around. Some books they're gonna give the area to the left of that one. Okay, let me see. I'll say on this one. Yeah, 3.841. So this is consistent with what we have. That means this table has given area to the right of that one. Area to the right of. Okay. See, this one, area to the right of. That means that so this one is same as, see, area to the, yeah, see, area to the right. This is alpha. Area to the right. Okay. Alpha. So in that case, see, degrees of freedom 1. Okay. Degrees of freedom 1, and then 3.841. 3.841. 3.841. Decision rule say what? If observed value greater than, see, observed value, see, then we're gonna say since x squared 0 is 900, observed value, which is 979. 979. .909 roughly or 10 greater than chi-square 1 comma 0.05, which is 3.841. We reject H naught and infer that there is an association between gender and exercise. Accept H naught, but we don't have enough evidence to accept H naught. But for time being at this primary stage, you're going to say you can accept that one. See, you can accept whatever you hypothesized, you reject that one and say you're going to say there's a this one you accept. But normally when you reject that one doesn't mean you can easily accept this one. You need more evidence. More evidence should be built up. That kind of a broader discussion you're going to build that develop that later on when you go to that you go to work or go to PhDs or research level, that you build up that kind of a heavy discussion. Whatever you reject doesn't mean that you cannot accept simply, but at that primary stage you're going to do like that. Rule. Or on the other hand, with the aid of p-value, by looking at the p-value, if the p-value is available, you by looking at that one, you can make the decision as well too. See, so that's that one. Then what else? Then see with this one, then show that your hand calculate chi-square and two conclusion on the presence of an association matches that produced by this one. Include the relevant frequency output in there. See. Okay, probability. See, probability already built up. See, this one 979.01 has been built up, and then from that procedure frequency, if you go to that one, see, you saw that one, they were already there. See, probability. See, the p-value is less than 0.001. So here that on the other hand, you can say, see, since p-value is extremely small, we reject H naught as well. H naught, you can go another way. See, you can use the second method too. As the second method is one. The first method or whatever that you can say. Reject H naught, and then you're gonna say there's an association between that one. You can say H naught, you can say nicely like this way, at the level of significance. Now you might be thinking why it's important. Yes, significance alpha 0.05 and infer that there is an association between gender and exercise. So why alpha is so important to this one? Look at, you see what you did was you reject H naught when H naught is true. See, look at what you did, the probability, reject H naught when H naught is true has been given alpha 0.05. That has been utilized. That's the size of the test. That's the size of the test. What's the power of the test? See, reject H naught when H naught is false. False. It's the power of the test. Power of this test. It's the size of the test. You might be thinking we can arbitrarily make this one smaller or larger In that way, we can build up the rejection region and get that our hypothesis that originally hypothesized that conjecture can be get rejected. No, you cannot arbitrarily change that one. It's going to affect this one. The power and size should be that, see, should be balanced. See, should be balanced. See, it's the power. It's the size. See, size of the test. Like a seesaw in the power from. You have to have a balance on this side. You cannot arbitrarily that increase this one. It's going to go down. Power of the test go down. In that way, it's not a good test at the end of the day. But anyhow, time being, you can take as it is. See, talk it on this one. Even the other stuff, even that we systematically talk about everything. See, another way to look at it. See, that's clear. See, see. This table, see, using data from exercise, this one, I'm sorry, that question number 3. What is the question number 3? Number 3, density. See, this one you can fill this in. See. Do you have calculator and include that and output in your explanation? For the subject, you can use this table. See, you can put the see. Normal, overweight, and obese, you can fill this in. See, in order to fill this in, you have to run again. See, so okay, let's go ahead and this plan. I need this one to out because I can see clearly there's the homework. What is the homework is, and then go to this one board. Okay, I can organize later that for time being that try to get this done. Okay, with that table, in order to get the table, you can get the table by what? You can get the exercise, gender, BMI for see, using this one. Table 1 for this subject. See, this is a table 1. Sorry, this is a table 1. See, table 1 has to be filling this one. Gender and exercise. See, the BMI by gender, by exercise. BMI by gender and exercise. We call that one now BMI. Can you remember? We don't call that one BMI cat. No. BMI for cat already over there too. It doesn't matter. It's not a big deal. But the BMI cat we're gonna call over here. See, BMI cat. See, 1, 2, 3 for cat. You keep that one. Doesn't matter. See, 1, 2, 3. If you want, you can say normal, overweight, and obesity. Those are the ones that changes like that. But if you go by BMI for cat, still that doesn't matter. So let's get this one and then confound us by the confound it. So this one. Not the right thing. So it's a table. You get the table. See, data. You go to the work temp. See the exercise and gender by. Is there no BMI for or BMI for cat? Doesn't matter. Those tables. The percentage, if you don't like this percentage, you can get rid of that one. See, no percent, okay. Same way that we see, can say no row, no column. See, that one, if you want, you can tell that. Some clean tables. See. Then since you need the percentage, I think that we can get the percentage too, because the percentages we really need, no, to fill this in. You need the percentage, the see, percentage for the normal versus this one. See, number and percentage, number and percentage. That means overweight versus gender, male, female. See, those numbers that you really need to fill this in, and they are p-values. See, if you get this one, set the table that you're gonna see. So I'm gonna go ahead and then keep rows, everything percentage. They will be useful. Okay. So this one, BMI versus exercise, BMI versus gender. So they are percentages, numbers, everything. See, you can bring this over here and then from this one and then fill this in. See, fill this in. Population, get the total population, their breakdown, percentages, normal versus male, normal versus female, normal versus years, no, overweight versus male, female, their number, percentage, obese, male, female, yes, no, see, you can fill this in. Okay, that one. Then what's the next one? Let's see. Write the results. See, you can say about the results. See, you can talk about that one. See, that. What percentage of female, what percentage exercised, what percentage that had a normal BMI, then there were proportion more female than expected in the BMI group. That kind of a discussion you can build up to. Say, up to. So, let me see. Here's the exercise. See. Consider. Investigate the confounding between sex and obesity by creating the binary variable. See. Binary variables. 0 and then using plus a 2 by contingent between diabetes and your new variable obesity. Show your hand calculation for the odds ratio for a diagnosis of this one. See, odds ratio and all kind of stuff. Okay, let's go to that one too. So the extra one. The hand calculation for see Cochrane, Mantle, and Hansel one. This one, all these hand calculations. See, diabetes being given by obesity and sex. See? So they are, I think that one. Okay. So then diabetes and investigate confounding between sex and obesity. And this time you can put the obesity. We check that one. No, we check with the table. See, 4 category BMI 4 category 1 category 2. See, city 0 and 1. these two together, see, obesity, you can, if you go ahead and look at our code, obesity, you can change that one now, see, you can change to what, that here we're gonna get the 1 and 2, see, 1, see, here my for category 1, 0, see, and the 4, 2 and 3 together, you can put, see, still put the 1. So then procedure frequency to contribute between a diabetes and your new variable obesity. See? That's a new variable confounded between sex and obesity by first creating the binary variable. We're going to bring it down to from that 3 option, it has been brought down to 2 option now. It will be brought down to 2 option. Then 2 by 2 contingency table between diabetes and your new variable obesity. Show your hand calculation for the odds ratio for a diagnosis of the diabetes with respect to obesity and interpret. Show your hand calculate 95% or confidence interval and interpret in terms of its width. Okay, so let's before we're gonna get into that one, I'm gonna show you. Let's go to this one. See, likelihood ratio. This is a likelihood ratio that chi-square test for association. Another association test is that normally. See, this is commonly reported by study software. The likelihood ratio chi-square G statistics. This has been given like this way. See, G squared. That's a chi-squared log. See, likelihood ratio chi-squared. You get the observed value, expected value, get the ratio, and then get the log on that one and multiply by each and every cells this the frequency. See, and this gonna be sum up over rows and columns. This means rows and columns this way and this way. Okay. So see, the Pearson chi-square and likelihood ratio provide the separate test statistics, but they share many properties and usually provide the same conclusion. When H0 is true and the expected frequencies are large, the two statistics have the same chi-square distribution and the numerical values are similar. So this should be even when we have a large sample, should be even distributed according to what? Chi-square. See? 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 Like that. This part has been done here. See? Each and every cell. See? Here. And later on, see? Later on that if you calculate this one, see, you can get this one 10.848. You can get by hand. That's another association strength. How strength would be Kramer's V. See, that chi-square divided by number this one, and K. K is the lesser number of categories, either variable in the contingency table. That means either number of categories of either variable. See, that's a minimum between the R and C. See, minimum between R and C. Okay, we can talk about this one too, mainly this. See, odds ratio. See.
Quick question, Professor.
Go ahead, yeah.
So, in an instance where it has, let's say, like three variables, how will we state the null hypothesis?
3 variables? Where?
Yes.
Oh, 3 variables when you have a, okay, you're talking about this one. No, let's say for instance, no, do we have anything like here? Okay.
Well, no, so I read it more carefully, and I think it's just asking about between the two explanatory variables. It's seeing if they're confounding. So I think the null hypothesis would just be related to those two, right? If I'm interpreting that correctly, right?
Yeah, yeah. Let's say that on the other hand, but if you have like something like this, okay, that 3 of them, let's say that mu of one group, another group, see, another group, the mu means like the wave that let's say that not related to this one, let's say 3 groups you have. So when you have like that 3 groups, whether they are averages are the same, versus you can say at least 2 of them. At least 2 of them are equal. Sorry, are not equal. Like that. So the here, like if you go ahead and look at here, see, so confounding between the sex and obesity, see, Confounding means like whether they're going to interact with each other. See, they interact with each other, and then it's going to affect to the diabetes. So normally confounding variables are the hidden variables. See, confounding between sex and obesity by first creating the binary variable and obesity. This one show you a calculation odds ratio diagnosis of this one. And
Okay,
the
since we actually generated a logistic regression model, how do we tell if the model is statistically significant, the overall model?
Oh yeah, overall one that's based on that it's p value. Yeah, that's a good question. It's based on that when you run that one. Let's say that we had that one. Sorry, I'm gonna go back to this one. See, then logistic regression. See, if you get this one to in that from the class notes that age cat, what happened? Okay. Age cat.
You may have to rerun those.
Yeah,
right?
yeah, that's why it's the whole thing. Okay, let's.
Sorry if I'm asking so many questions.
No. That's the way that I like to have the class like that way. We have to have a broader discussion, not like a teaching, because it's keep going. Here, see, p values, see, p values, see, p values, see. All the p values are given, and then you're gonna see whether exercise gonna explain, gonna affect to the diabetes or age category. See, age cat again intercept the exercise and gender. See.
Yeah,
So,
but that's at the variable level. So that's giving the indication for each individual variable. What do we look at to determine overall model performance?
overall model, yeah. Let me see here. Where is that? Likelihood ratio test. See here. This one. This is the one. See. This
I
is one
got
of the method.
you.
Yeah.
Likelihood ratio.
Yeah,
Got it.
likelihood ratios. Yeah, likelihood ratio can be utilized in order to make that p value. You can utilize in order to do that one, or you can get this chi-squared value can be that's the observed chi-squared value can be compared with the critical chi-squared. Same thing that I did over here. Always two methods. You have two methods. Always you have two methods. See. Either you're going to compare contrast. That chi-squared value is the observed chi-squared value. This is called the critical chi-squared value. It's based on your degrees of freedom and that area to the, normally we get alpha 0.05. You can make the rejection on that one too. Okay? That's a kind of because this is very challenging because this course has so much material involved here and there. We have to bring it to one place and then make it very clear cut at the end of the day. So the big challenge ahead of us is the time. That's the serious issue. Time is the biggest problem. Yeah. So that individually, even that you can check that one overall, as you said, that overall we can have a look at it. See, so many things, but we have to go because they were scattered all over the place. Eventually, what I'm trying to do that with the even by Friday, thoroughly go through this one along with that all that codes. Coding is not the biggest issue. Issue is that how to get this interpreted at the end of the day. See. But when overall come everything, that's a lot of work. But in addition to that one, like real quick, that if I jump and show you that this look at the in-class exercises. Do you see that in-class exercises? These two, I made that one available too. See, class exercises. See? Something we can that at the same time we can jump and back and forth like a little bit everything, and then we can stop for today, and then we can meet Friday, and then pretty much finish everything, taking at least like 3 hours. I think we need the whole block of time. So this one, do you guys see this one on your homework? That sorry, class exercises. So this is a class.
Just to confirm, we're being graded for homework and we're being graded for progress checks, right? Not
Progress
class.
check only, not this one. No,
Okay,
not this one. No, not this one. You are right. You are on the right track. Yeah. Progress that check and this one only. The progress one. Progress one. Is that the progress one? See, it's the progress one. Oh, that's other progress one that I have seen. See, you have to do which of the following is true, that true or false, and I can help you out for this kind of stuff too. So that's why we have to know that very clear cut that when we do one thing that very clearly built up this piece by piece, that this all the information, because there are so many readings you have to read too within 1 week, that so many textbooks, so many contents. At the same time, everything has to be done using R, SAS or Python, doesn't matter. That one too. See, different books, see, they have that or so much explanation. See, at the end of the day, see. But I'm trying to do systematically get piece by piece to the one place and then explain everything at the end of the day, because that eventually I talk about the logistic regression in a large scale. So here, look at that. If you get back to this one, you know how to do this one for sure. See, then the show you hand calculation for the odds ratio, because we were talking about the odds ratio, get like a rough idea about the odds ratio. The odds, we're going to talk about the odds and then we're going to go to the odds ratio. So here, see, the strength of an association can also be measured by the odds ratio and the related concept of the relative risk. There's another two risk, there's another concept. Consider again the outcomes of related to this example, okay? The odds can be an event occurring another number of times, it occurs divided by number of times it does not occur. We know that one, see. Something gonna occur, see, if you're gonna go ahead and in the case of our clinical trial, the odds of the drug treatment having a positive outcome. Drug treatment having a positive outcome is 45 divided by not having that one, see. Drug treatment having a positive outcome, 45 to that or 1.1 to 1.5. See, so see, you can make it like a ratio, like a 3 to 2, like that. See, you can expect 1.5 times as many positive outcome versus negative outcome when given the drug treatment. When given the drug treatment, see, positive to negative, see, occurrences to non-occurrence. See, that's a probability of the outcome or non-occurrence. Probability of the non-occurrence called the odds. This one. Then on the other hand, with the aid of this one, if you want to go to the probability is nothing but odds of the positive outcome occurrence divided by the 1 plus the odds of the non-occurrence of that particular event. But whatever you are interested in getting positive, see, drug and positive. This is the occurrence. Its counterpart is this guy. If you are having this one, its counterpart is this one, placebo. See, based on how you're going to look at it. By solving this one, you can get the P. See, probability. Like that. Then they're going to go to the odds ratio. Odds ratio means at least, see, having lie between, sorry, the workforce of summarizing the strength of association in contingent. In drug exam, the odds ratio for the drug having a positive outcome is simply the ratio of 2 odds. 2 odds. What are the 2 odds? See? Odds ratio. Or, see, the probability when it's constrained liability is 0, and however, although the bounded on the low end at 0, the odds of that event have no upper bound. See? And make it easier to make comparison. If the probability of drug A having a positive outcome is 25 times, and that of drug B is 75%, we can conclude that the probability of positive outcome from drug B is 3 times that of drug A. That kind of a comparison you can do. But we cannot say that the probability of positive outcome for drug C is 3 times that the drug B. We are constrained by probabilities having lie between 0 and 1. 0 and 1. So the odds ratio means like then you get the ratio between the 2 odds. See, odds. See? So the standard error of the odds ratio has been given in order to build up the confidence interval. See, odd ratio, see, confidence interval odd ratio is, they have written like in this way. See, you can build up the confidence interval too. See, exponential, see, and the see, ln of odds ratio 1.96, standard error of this guy, put it over here and then put that one. So that means that if you go ahead and calculate the estimate of the precision, see, that means like when you get the odd ratio, is the odds ratio should have some kind of a, as I said over here, not only for that one way, one person's that sample, if it had been, had this been done by the several people, how would it gonna vary from that odds ratio to odd ratio from that different samples? That the variance is called the standard error. It's nothing but one way, CD, A, B, C, D are the cell frequencies that you can remember that in the beginning they have taken A, B, C, D. Those are cell frequencies. That's okay. Should be A, B, C, D. Those are the cell frequencies. It's not related to probability the same way. This one we saw that one. And summarizing the strength of an association is in our acne drug tricker, the odds ratio for the drug having a positive outcome is simply the ratio of two odds. See, the drug having a positive outcome. See, the odds of the drug treatment leading to a positive outcome over the odds of the placebo treatment leading to a positive outcome. These are the two odds. See, that means that we are talking about the odds. See, for this guy and this guy. And especially which are two odds that we're going to take into account. See, the odds of the drug treatment leading to positive outcome versus over the odds of the placebo treatment leading to a positive outcome. See, that means this odd here, this odd and this odd. See, how do you find the this odd? See, this odd. How do you find the this odd? That see. The drug treatment leading to positive outcome. Drug treatment leading to positive outcome. The odds of drug treatment leading to positive outcome is what? 45. See, divided by 30. See, this one. But it's a probability divided by, you don't have to worry about the probability. If you get the probability 45 over 75 divided by 30 over 75, 75 get cancelled out. That's why simply you can say 45 over 30. See? That one. And see, on the other hand, for this one, 25 over 50. See, 25 over 75, that's the probability of the occurrence divided by the non-occurrence, negative results. So that ratio, see, this ratio and that ratio, one is 1.5, the other one is 0.5. That division, see, that ratio is called the odds ratio. We conclude that someone receiving the drug treatment will have a 3 times the odds of having a positive outcome related to someone receiving the placebo. See, we can talk about the odds. See, 3 times the odds of having the positive outcome. See? Someone receiving the drug treatment. See, conclude that someone receiving the drug treatment will have a 3 times the odds of having a positive outcome related to someone receiving the placebo. See? Another way to say this is that the odds of having positive outcome are 200% greater. See? 3 minus 1 times if one receiving the drug treatment. That's the odds ratio. So OR can equal any non-negative number or implies that no association between the row and column variables. OR value further from 1 in either direction indicates strong association. OR symmetry, this is the indicator. By looking at this one, you can check that association at the end of the day. And not only that one, now we are, instead of, since we get to that estimate, these are estimate. Now you need the what? You need this, it's a standard error. Standard error means the estimate standard deviation of this guy. Standard, now you might be thinking it's a fixed value. How come? As I said earlier, that if you had done this one 1,000 million times, the OR values you have calculated not going to be the same. That variation can be put it into a histogram. From the histogram, you go to the center point. That center point will give you the observed one, which is this one. And not only that, you get the spread after that histogram, which is called this one. Okay? Which is this one. Okay? Since you're going to have the formula has been built up for the LNOR, you're going to get the exponential when you write the confidence interval for the OR again. See, you take the exponential. So your bounds going to be the exponential bounds going to be from here to here. So all the time the standard error means 1 over A, 1 over B, 1 over C. These are the frequencies, cell frequencies. See, cell frequency. This is A. I'm sorry. This is A, B, C, D. A 35, 30, B 45. See, C, D. See, like that. So that's the standard error they were talking about. So this, see, odds and odds ratio. This means odds ratio OR. So OR can be utilized in order to see that association between two variables. So OR, see, when you get the OR means, see, O, O1 over O2, see, like that, odds over odds. Then you need the standard deviation of OR or the standard error of OR. This has been taken with logs. The formula says like that: 1 over A plus 1 over B plus 1 over C plus 1 over D. 1 over D. So that means here in this table, see, A, B, C, D, see. And the confidence interval for what? OR. At how much level? Level of confidence 0.95 is nothing but OR. I'm going to say lower bound. I'm going to write this way for you to see clearly. Lower bound of OR, comma, upper bound of OR. See, the endpoints are included. I'm going to put the brackets. See, endpoints are included. Brackets. See, this sent to other end. See, see, it's one lower bound or lower boundary, upper bound. That's the confidence interval. This one confidence interval. This one confidence coefficient. Confidence interval. This is a confidence level or coefficient. 0.95. That confidence interval, if you write that one, they say that can be easily get it by what? See? This formula, see, this formula, see, 1.96. Where did you get the 1.96? This is assuming that this will be distributed according to a normal distribution. That's the key part here. This is coming from normal distribution. How much? 95%. So they believe that when you have a OR is normally distributed. Sorry, LNOR. I'm sorry, LNOR, normally distributed. Okay, that's why they take the exponential over here. So LNOR, see, LNOR distributed with normally distributed. See, normally distributed with its own mean. See, own mean and standard deviation. What is the mean? Mean is nothing but ln, okay, log OR observed value. See, observed value. That one you have, that one in your hand. Standard deviation is what? Standard deviation squared, okay, squared. So standard deviation is what? Square root 1 over A plus 1 over B plus 1 over C plus 1 over D. That kind of a normal distribution, see. That's why it's fitting into that one. You get the center. Center, you have what? This is, you're going to talk about in Z. You can convert this one into, later on, you can standardize. Same thing. You can standardize. See? You can standardize. Same thing you can say LN or standardizing Z. Z means 0 and 1. Standardized normal. See? Standardized normal. You standardize. The center you have, see, center you have what? If you want, you can go with the Z or you can go with the LNOR. See? The center would be, you have LNOR of value. This spread is nothing but this one. See? That's the one. You got this one from what? Histogram. By drawing the histogram for all the LNORs, you got that one. That's why you get the 1.96. 1.96 coming from what? 6 is, see? You can remember, see? You have it like this. This one is in the middle, you have 0.9, see, confidence region. It's a confidence region, see? If you want, you can say alpha over 2 over here, 0.052, 0.025, or 0.025, this side too, for one side. Anyhow, this value is the critical value for Z, which is 1.96 related to that. That's how you get the 1.96. That's why they're going to write, normally you can write the lower bound of LNOR like this way. LNOR observed value. See? That's what they were doing over here. LNOR observed value plus, sorry, minus 1.3 OR observed value. See, in another way, I can say LNB. OR means estimate plus what? Margin of error. You can remember. Margin of error. The maximum error that can occur. Max error. Max error. Margin of error. That's the margin of error. Margin of error has been given by standard error of, see, LNOR times Z critical. C critical. See, so you have LN OR ops value plus, I'm sorry, minus. Okay, lower bound is minus. I made a mistake here. Minus, 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 minus. Standard error is 1 over A, 1 over B, 1 over C, 1 over D times critical value is 1.96. See, later on, you don't need this one in LN because that's why we have to make sure we're gonna write the confidence interval in LN to be taken out. That's
Professor,
why.
real quick, I gotta go. Thank you very much.
Yeah, because I'm gonna stop here too because we can continue the same discussion again on Friday. Okay. If you miss the class by any chance that you have that recorded video that you can have a look at it. We keep continuing this discussion because all the parts should be bring it up to one place at the end of the day. Okay.
All right, thank you very much, Professor.
Anytime. Okay. Have a good night. Okay. Good night or good morning. Anything. Okay.
Thank you. You too.
So here that. Sorry. Here that if you see, that's why they put me exponential from outside. See, exponential. See, for the whole thing, you're gonna raise to the exponential. We'll give you the lower bound. See. So I'm going to put EXP over here because it has been taken with the LN to be taken out at the end of the day. The theory has been built up with the LN has to be taken out. That's why we're going to take the exponential after you take a whole thing over here. See, so for the formula, If you plug in into the formula, you get like this. So the similar fashion, you have to do the same thing in your that homework. Homework they have asked the same thing. So what we're gonna do, see, ln this one, you get the exponential. I'm gonna put here exp. See, whatever that you get, that one exp for this one and this one too. I'm gonna make this one very clear. I don't need that one for ln. If I write this one for lnor, I'm gonna write for the lnor first, and then I can write like this. That's okay. lbo lnor, lnor comma upper bound lnor. That's for the natural log one. I don't need that one for natural log. My confidence interval. I need the confidence interval for OR. Because of that, I'm gonna do this. Gonna be raised to the power of ln lb lnor. That one I'm gonna get this. It's a power of exponential. Okay, so exponential upper bound of lnor. See, lnor, whatever you have later on, that you're gonna get that one and then find the exponential. So I'm calculating for lnor. lnor, lb lnor, then lb lnor means lnor observability.
Sorry, sorry, Professor. I'm going to have to be leaving. Just want to let you know I'm heading out as well, Professor.
Sure. Okay. Thank you. Okay.
Right, thank you.
I'm gonna. Yeah. Then we can continue the rest. Okay. The next time. Thank you. Yeah. Thank you very much. Yeah. We can continue the rest next time and then continue from here and then go through all the answers. Okay. One by one. Thank you. Take care. Bye. Good night.